Hi, everyone, and thanks for having us today. We are happy to welcome you to the inaugural webinar for the iStructure Pan African Knowledge Partnership. A quick introduction about me. I am Gabriel Macaulay, a registered engineer in Nigeria, member of the Nigerian Institution of Structural Engineers, and since 2024, I've been a member of the iStructure Humanitarian and International Development Panel. Career wise, I've been privileged to have worked in the oil and gas industry, the energy industry in Nigeria, where I have gained immense experience in designing structural entities, basically reinforced concrete element and steel structures, and also I've led a team of engineers consisting of interdisciplinary engineers in achieving critical energy infrastructures within Nigeria. Later on, I transitioned to the United Kingdom, where I am currently working as a technical lead on a low carbon energy project, which in part is geared towards attaining Britain's 2050 net zero goal. So, quickly for the topic today, I have with me Jenny Burridge, the head of education and training at the Concrete Center. Jenny is a fellow of the iStruct and a chartered civil and structural engineer. Also, I have Cam Bailey with me, Director of Engineering Mass Design Group based in Rwanda. Cam is a chartered engineer with iStructure and as well with the Institute of Engineering in Rwanda. And he is a sustainability enthusiast and he has delivered a lot of award winning projects across the sub Saharan Africa. Also with me today, I have Dr. Ron Watermeyer, Director of Infrastructure Option, a doctorate degree holder from the University of Witwatersrand in South Africa. So they will be helping today with the presentation on the topic applying the principle of link concrete design. So a quick one for the webinar housekeeping on the video that you may be on the video frame that you may be seeing, right beneath it, beneath the video frame, we have the CC. That's a closed caption which you can toggle on and off to enhance subtitle of this discussion. And as well, if you look at the right hand side on your screen, you should be having the overview. Under the overview, you can see how to resolve in case you have issues with video or audio. And in case further support is needed, you can email event at istructure.org. And also, resources are available right beneath the overview for you to access some of the information that we're going to be presenting to you today during this presentation. And to let you know as well that the recording for this presentation is going to be available as an on-demand resource in 2 weeks' time. And we have some copyright information on the screen as well, which may interest you. So quickly, what battered the discussion that we're having today, this webinar, is iStructure's Pan-African Structural Engineering Knowledge Partnership. And in the word of Yasmin, the CEO of the institution, which iStructure's vision basically is to ensure that structures built around the world are safe, resilient, and sustainable. So, in that light, it becomes important for the institution to collaborate with international partner, and that is being done through partnership with Commonwealth Engineers Council. And for the pilot stage of this partnership, 10 African professional engineering institutions has been selected for the pilot scheme. And for detail of the partnership, for access to resources which the selected PI are going to be enjoying, and for student membership, for affiliates membership that we have, I will encourage us to go to the resource section under the overview that I earlier discussed to access some of this information. And if you have any further question, you can send the mail to the institution through the email on the screen. And maybe for further information or detail about student membership, you can you can send an email to education@istruct.org. Now to the big topic of the day, which is applying the principle of lean concrete design. Why do we need this? So basically, it's known that new build globally on a weekly basis, the construction output on a weekly basis in the new built environment is equal to the size of the city of Paris. And from iStructure publication, if you check on the right-hand side of my screen, we have the value for the CO2 equivalence of 1 cubic meter of structural concrete. If you we can see at the bottom left of the screen as well, we have the estimated infrastructure concrete volume to be around 50 to 100 million cube. And that means that's the extent of the new build that we have on a weekly basis. So I did a very quick estimation, approximate carbon estimate for that, and using the lower band of 50 million cubic meter. That means if all engineers that are here today or all players in the construction field, we can target like 10% reduction in concrete volume in all our designs. Definitely, we're going to be saving a reduction in GHG of around 2.15 million ton of carbon CO2 equivalent, which is like equal to like a reduced carbon equivalent of around 500 average family car running for a year, or around 1,003 one-way flights from London to New York. So that's it. So that means for us, we can actually, in our various space, have impact with our action to reduce GHG emission on a global basis. So that said, I'm more than excited to hand us over this afternoon to Jenny for our presentation. So Jenny, are you good to go, please?
Thanks, Gabriel. So in my presentation, I'm going to talk with giving a short introduction to basic concrete construction. I'll then look at the range of concrete frame options, and then I'll move on to what we can do to improve the material efficiency of our structures. And I'll finish by giving a worked example. With concrete, the range of concrete construction approaches available. In situ construction, which is the common one, is where concrete is poured on site in the position in which it will be used, using formwork as the mold. It has inherent robustness and allows modifications on site, but it is generally slower. Post-tension concrete is a method of adding pre-compression into concrete after it's been cast. This pre-compression significantly reduces the tension steel required and enables the concrete to work more efficiently, saving up to 20% of the concrete and 50% of the steel. Precast concrete is concrete which is formed off-site, typically in factory conditions and brought to site for assembly. Elements can be either standard, proprietary components, or bespoke elements designed to suit a particular project or application. It is typically very fast on site, but precast concrete elements should be repetitive so that it enables molds to be used again and again, and minimizing cost and waste, which is important. Hybrid concrete construction uses the precast and in situ together, combining them to give a robust, durable construction system with reduced time on site. As you can see from this picture, there are lots of concrete frame options depending on the type of concrete construction you are using. I'm going to talk about floor slabs in particular, because that's where an awful lot of the material is if you're looking at a building. I now want to look at how to improve material efficiency. The building grid has a significant impact on material efficiency. This graph shows rib slab depths at different loads and spans. Typically, increasing the span increases the structural depth, requiring more material. For example, at a load of 2.5 kilonewtons per square meter, increasing the span from 8 meters to 10 meters, it leads to approximately 125 millimeter increase in structural depth. In other words, increasing the span by 25% increases the slab depth by over 40%. However, we don't see this trend everywhere. In shorter spans, the structural depth is often governed by practical construction limits. When it comes to proposing shorter span lengths, this may go against client or design team aspirations for flexible, relatively column-free spaces. In particular, in open plan, say in open plan offices. However, it's acknowledged that this can lead to carbon-intensive structures, and it's worth pushing back on having very long grids. It's not just the span length that impacts material efficiency. The layout can also have a big impact. The aspect ratio of the bay, for example, how square or rectangular it is an important consideration. And square bays are typically more efficient for two-way spanning slabs, whereas rectangular bays are generally more efficient for one-way spanning systems. Although selecting a regular layout, through selecting a regular layout, we can increase repetition, which can speed up the construction and allow for reuse of formwork, which can reduce the wastage of formwork on site. Structural depths are typically driven by the worst case span, and typically the worst case span is at the end span in a continuous structure. To improve the material efficiency, you may want to consider reducing the spans at the end bay or introducing a cantilever at the slab edge, both of which will give you more efficient structures. If we return to the graph we saw earlier, we can see that the load on the structure also impacts the structural depth and material efficiency. For an 8 meter span, we can reduce the imposed load from a 5 kilonewton square meter to a 2.5 kilonewton square meter. We reduce the slab depth by about 50 millimeters. The loads on structures are determined from a number of sources, such as client requirements, codes and standards, experience and industry guidance. So it is important to consider where there are opportunities to refine them. With these images from the MIICON project, which were published in the Structural Engineer a few years ago, these are really helpful for understanding and visualizing what the different imposed loads mean. One of the concerns with reducing the design imposed loading is that it may limit future flexibility should a project be used for something else. The decision to allow for future flexibility should be made on a project-by-project basis, but where possible, we should avoid over-designing structures and consider strengthening it if a greater capacity is required in future. For imposed loads, designers should also consider using live load reductions for buildings over 3 stories, as this can lead to material savings in the vertical structure and the foundations. We saw earlier that there is a wide range of framing options available, and identifying the best framing solution for each case depends on a number of factors. Typically, deeper systems, such as rib slabs or slabs on beams, are more material efficient than shallow systems, such as flat slabs. Beams can be used to support large point loads, and flat slabs are more appropriate for regular column grids, and they're not suitable for large point loads. Structural systems that incorporate voids, such as ribs and waffle slabs or precast hollow slabs, minimize the use of concrete where it's not required. And post-tensioning should be considered wherever long spans are required, and that's about over about 7.5 to 8 meters. Post-tensioning should be considered wherever possible, in other words. Hollow core planks typically use pre-stressing, so they've got pre-compression and they are material efficient. These graphs show the embodied carbon and depth of the structure for different floor systems. As can be seen, there isn't a one-case-fits-all solution. It depends on the requirement of your project. Whilst factors such as span, loading, and structural floor systems can have potential to make material savings across the frame, the opportunities to improve structural material efficiency as part of element design should not be overlooked. It is common for designers to group elements such as beams and only design for the worst case. This is then used for the element size and reinforcement for a whole group of elements. This rationalization is often used, but does lead to use of significantly more material than is actually required. Designers need to find a balance between enabling design and construction to be efficient and accurate, and avoiding unnecessary material use. Engineers should also consider opportunities presented in the design codes for refining designs, such as detailed calculation methods for deflection, which may enable a shallower beam or reduction in the reinforcement, or the calculation of lap lengths and anchorages of lengths should be based on the actual bar forces, not on standard tables. That allows you to reduce the reinforcement quantities. You might consider looking at partial safety factors when using the design. We did a study using UK CARES reinforcement data, which showed that it is feasible in this case to reduce the partial safety factor of reinforcing steel from the recommended value of the 1.15 in Eurocode to 1.05. This is for bending. This potentially reduces the area of steel required by 9.5%, although it may be affected by other demands such as robustness or serviceability. When selecting our framing option, we need to think beyond the frame itself and its wider impact on the building design. The structural design can lead to other opportunities to reduce program, cost, and carbon, and these are important to consider as part of the decision-making process. Some of the key opportunities are reducing the floor depth, which can make the overall building shorter, and this can then lead to a reduction in the height of the cladding required and the cost and carbon associated with that. The design of foundations is highly dependent on soil type, ground conditions, and site restraint. However, reductions in foundation loading will enable cost and material savings to be made in the substructure design. In schemes such as where a flat soffit is provided, the installation of partitions may be simplified. For example, there's no need for cutouts around downstand beams, which can avoid wasting partition materials. Additionally, flat soffits can allow for more efficient services routes, as there is no need to route around downstands. These shorter routes can lead to less ducting and other materials being required. Where soffits are exposed, we can use the thermal mass of the structure to reduce operational carbon. This is even more efficient for options such as ribbed and waffle slabs, which have greater surface area. Finally, through exposing concrete within the building, we can reduce or remove additional finishes such as ceilings and the cost, carbon, and installation time associated with them. Now we have a spreadsheet. This is the Concrete Centre spreadsheet that considers the structural frame options available and can rank them in terms of cost, program, and carbon. It can be downloaded from our website using these details. And on the download page, you'll find a how-to webinar, and that includes a full work example and a how-to guide to help you get started. I'd like to take you briefly through a work example now to see how incremental changes can make a significant difference to the material efficiency of a project. The baseline for this example is an office building with a 9 by 9 meter grid and imposed load of 5 kilonewtons square meter. It's a flat slab with a depth of 325 millimeters and has an embodied carbon of 112 kilograms of CO2 per square meter. And we've used a typical concrete mix for this example. And the concrete itself is the same in each of these options. So the savings in carbon are just from the savings and the changes to the structural system. Further savings can be made by changing the concrete mix. The first step is to reduce the imposed load. So with the recommended imposed load for offices in Eurocode is 2.5 kilonewtons square meter, and then 1 kilonewton square meter for partitions. So if we reduce the imposed load to 3.5 kilonewtons a square meter, to align with this, the slab depth may be reduced to 290 millimeters, leading to an embodied carbon reduction of 11%. The second step is to reduce the column spacing from 9 meters to 7.5 meters, keeping the footprint of the building the same. In combination with the reduced imposed load, this results in a 25% reduction in embodied carbon compared to the baseline scheme. And the final step is to change the structural floor type to a waffle slab. The combined changes in column spacing, loading mean that the proposed waffle slab solution is in fact 290 millimeters deep compared to the 325 millimeters for the flat slab in the baseline scheme. And there's an embodied carbon reduction of 42%. This also offers more space for floor build-up and surfaces or opportunity to reduce the overall building height. The increased surface area provided by the waffle slab enables greater potential use of thermal mass for heating and cooling. To conclude, we looked at the range of concrete construction types available to help identify the approach that suits your particular client, project or site. We then looked at a wide range of concrete frame options and the benefits of each of these. Optimizing the design criteria will help improve material efficiencies, and there are resources, including Concept, to assist with comparing these options. So that's it from me. I'm now going to hand you over to Cam Bailey.
Yeah, thanks, Jenny. Hi, everyone. I'm going to talk briefly about our project, Grafenal Hospital. It's a new 200-bed, 16,000 square meter healthcare facility in Luanda, Angola. To begin, I'll just give a brief overview of the structure. The architectural layout is arranged around a central courtyard with 4 3-story wings housing different programs. Going clockwise from the bottom center of this image, we have the main entrance, 2 L-shaped ward wings, and the larger clinical wing on the right. In situ reinforced concrete is the main building material in Angola, so we adopted this to form the primary structure, but combined it with a steel roof to achieve the large overhanging canopies above the entrance and the central courtyard. To accommodate the medical program, we adopted an 8-meter structural bay throughout at an early stage, and the building is founded on shallow pad footings. We had a number of different conditions in section. Here you can see the stepped profile of the building, 2 of the central cores, the long span steel truss over the courtyard, the cantilevering truss canopy over the atrium at the entrance, and just a quick diagram showing vertical load bars here. With a large building footprint like this, an efficient lateral stability system was important. We centered primary cores around the central circulation space of the courtyard, then introduced independent shear walls at the extremities of each wing. This approach avoided the need for moment frame systems through the beams and columns, which can drastically increase concrete and reinforcement quantities. This freed up the columns and the slabs to be designed as efficiently as possible. So now I'll just talk specifically about the waffle slab system and the lean design approach we took. So to achieve the 8-meter bay size, we proposed this 2-way spanning waffle slab system with drop panels above columns to resist punching shear. The waffle slab molds available in Angola are typically 800 by 800, which fit with the 8-meter by 8-meter bay size. They're often imported from Portugal or China, and they're removable, reusable, and use a proprietary propping system. However, we found that fire resistance requirements were driving the dimensions of the waffle slab rather than the structural capacity. Healthcare facilities often need 60, 90, or even 120-minute fire resistance, but we were at the lower end of this due to the building only being 3 stories. According to Eurocode 2, Part 1.2, whether you are designing a waffle slab or a solid slab, to achieve a 60-minute fire rating, the slab must be at least 80 mil thick. The ribs of any waffle slab must also be minimum of 100 mil wide, no matter the span. So we decided to explore what it meant to push these minimum dimensions for fire, particularly the slab thickness, towards the structural capacity. An 80 mil thick slab can easily span 1.2 meters square, even with a relatively high imposed load. An 100 mil thick slab can easily span a 2 meter by 2 meter bay. So we analyzed various rib spacing, which were divisions of the 8 meter typical structural bay, including 0.8 meters, 1 meter, 1.6 meter, and 2 meters. We carried out structural sizing exercises for each case. The 0.8 meter rib spacing required a 450 mm deep rib with 80 mm thick slab. And at the other end of the scale, the 2 meter rib spacing required a 525 mm deep rib and 100 mm thick slab. After calculating the resulting material quantities at the schematic design stage, we could demonstrate that adopting a 2 meter rib spacing rather than the standard 0.8 meter could lead to a 25% reduction in concrete volume and a 30% reduction in total reinforcement. Of course, we had to acknowledge that this would be a non-standard system and that special molds would need to be fabricated and shipped to Angola. However, it's worth noting that wider rib spacing is not a new or revolutionary concept. This type of construction has been used elsewhere, and there are manufacturers who are used to supplying this type of formwork. We received quotes from Cordec in the UK and Technic Calip in Turkey, both providing molds that could allow 10 or more reuses. Cordec proposed an expanded foam material, which was more expensive and bulkier for shipment, and so we opted towards the Technic Calip product, who proposed reinforced polymer, more similar to the readily available molds in Angola. These were more cost-effective and could be stacked for better shipment. We updated our numbers through the design development stage. You can see here that the top of the table, that the rib sizes increased in both cases due to a more detailed analysis having been completed, including more rigorous deflection and resonance checks. Cost analysis included amounts for formwork and waffle molds established through direct quotations, as you saw, and with the QS on the project. We found that the 2 meter rib spacing led to a roughly 10% cost saving from the standard waffle system and a 30% reduction in embodied carbon due to lower material quantities. We also believe that the time on site would be significantly reduced, with less rebar fixing and many less fiddly junctions between the ribs. And then a final consideration is the effect of this on the weight of the building. Due to the reduced material quantities, the total load on each floor level obviously reduced as well, by an average of around 13%. For areas with lower imposed load or lower partition loading, this percentage reduction was higher. This has a knock-on effect on the size of the pad foundations. In areas with a steel roof, we demonstrated potential foundation area reduction by around 15%. And in areas where we had 3 levels of the waffle slab construction, such as below service roof areas, the reduction is more like 19 or 20%. In reality, given the 300 kPa bearing pressure we had on site, this meant reducing these larger pads from 3.5 meters square to 3.1 meters square. Assuming these are 0.6 meters deep in both cases, this would save around 1.6 cubic meters of concrete per pad. And with a building with such a large footprint and so many columns, the total additional material cost and carbon saving potential is very significant. Unfortunately, despite the evidence, the contractor on this project decided to stick with what they knew and use the standard off-the-shelf waffle slab system with the 0.8 meter rib spacing. And so on that note, I will hand over to Ron, who hopefully will talk us through some of that. Thank you.
Thank you. I've been asked to talk about the influencing clients and contractors to achieve lean design. I think let's just start off with the fundamentals of project delivery, how we deliver, because at the end of the day, it's a buying and a selling process. A client wants something and a contractor and designers will provide it. So if you look at the starting point, you're going to have a client value proposition or the promise of measurable benefits resulting from the project. And if you go to the finish line, you're going to have project value, which is the outcome of client decision-making to achieve an optimal balance of project benefits, risks, and costs. So to get from the start to the finish, you're going to have a client value proposition, which is going to reflect the client values, satisfy a business case, the budget, time for completion, scope, and then very importantly, one is going to have to procure resources to deliver the projects, go through your project activities, land up with your end product and all the sustainability impacts. And through that process, the client needs to perform a delivery management function, which is really the influencing practices, because their fundamental role is to plan, specify requirements, procure resources, and oversee delivery. So in this process, what the key issue is, if we're looking at lean construction and we want to maximize value and minimize waste, and I think some of the two previous speakers were talking very much about that, we need to minimize the gap between what was planned and what was delivered. And there's a very good example that Cam gave of you design something and contractor decides he's going to do it some other way. So really the focus is we want to get rid of fragmentation where we have them and us, or a separation between design and contractor, and we want to move the two together to work collaboratively. Now, a paper that struck me many years ago in my journey through a lot of these things is Lichtich indicated in 2006 that to provide higher value and less waste, the fragmentation in design needs to be addressed, and he spoke about preferably before 25% of the design is complete. What I've shown in this diagram here, if we take the stages in a project cycle where you're going to have your preparation and briefing, concept and viability, design development, until you come into the works. And if I link it to the association of the AACE International, the Advancement of Cost Engineering, and we look at what they've got, their class estimates as you go through, and the degree of maturity in the project, you will see that if you're looking at the 25% mark, you're well into the concept stage. And by that stage, sometimes we've lost what we need to achieve. So we need to think about this, how to get contractors involved in construction at an earlier stage and participate in the design process. So we've come across the concept is early contractor involvement, where what you want to have is the principal contractor engaged at an early stage to offer input into the design process, to get buildability, to get design, and to optimize value, minimize waste. Now, we do have some models, and depending upon which part of the world you're in, some of them are more popular than others. You can have the design and construct, which takes place after the concept and viability, perhaps a little bit late in some aspects, develop and construct, design by employer. But what does tend to happen is that even though they try and reduce the fragmentation in relationships, sometimes in the tendering conditions, there's just insufficient time to work collaboratively under tight deadlines, and the concept design is too far developed to reverse it to get something better. So we've got to think about trying to do things in a different way. So there is the concept of early contractor involvement, which I will take you through. That's part of the NEC Engineering and Construction contract. They have an option for it. And the idea of that is that you would, after you've done your briefing or your strategic brief for your design for, to take your project forward, your contractor would be appointed at the same time that your designers start working on it. And so you split the activities into stage 1 and stage 2, where stage 1, you'll go through all the design process. When you've got what you're going to build and you're going to enter into your construction phase, the client would then instruct construction. So you would move through all the way through the stage 1 and stage 2. Stage 1 would typically be on a cost reimbursable basis. Stage 2, you can do on a target cost basis. For those of you that are not familiar with target costs, because the problem is if you're paying on a cost reimbursable basis, there's no control on productivity. So the idea of it is that you would set a target at the outset. You'd pay the contractor his cost uplifted by his profit and overheads. When you come to the end and you come to completion, you will see, are you above the target or below the target with costs? And what you would do is you would then share the pain and gain. So there's an incentive for both the client and the contractor and everybody to work within the budgets that are put together. So this is one method of providing an opportunity to engage a contractor earlier to get lean construction going. Another way of doing it is something that I've been involved with a number of years in South Africa, where we've developed framework agreements in a single phase approach. In other words, what happens is you have all the terms agreed in the contract. and you then call off orders. So an order read with the standard terms in the framing contract would then create the contract that you can move forward. You'd have a start date and an end date, typically a 3 to 4 year period, and you may issue, the rules of the game is you may issue as many orders as you want from the start to the finish of the term, and anything that you start before the term you will finish, and then the contract will come to an end, but you don't instruct after that. So what this does is it allows you to also achieve an appointment of a contractor while the design work is done, even if you have a separate contract to do the design work and have and no responsibilities for the contractor to do design, if that's the way you want to do it. So with this, it allows repeat relationships to work. So if you're working across like a campus, a university campus, schools, or anything else like this, you can start off with a first order, and you work with the same team order to order to order, and so you can improve your techniques, improve your ways of trying to get better performance. If we then look at just to try and just bring this to an end and just put some sort of remarks and observations, because I've just had time to introduce you to some of the concepts. And I think that, to me, lean design will only be realized when designers and contractors collaborate. And that is where you're going to get the best results out of it. And that is where you need some early contractor involvement is essential. And remember that procurement is, after all, a buying and a selling process. And if we can get that right with the right objectives, we will then be able to deliver. But I think just some of the things we need to think about in trying to influence the change is I really believe that clients will only change their approach to procurement when they are dissatisfied with the project value that they realize. And I think we've got to start publicizing some of the bad projects where you haven't realized the value, to encourage people to do the good value and publish those as well. We also need contractors and consultants need to demonstrate the benefits of early contractor involvement to realize better value. And a culture change is necessary, and cost-based pricing strategies need to be embraced rather than avoided. Particularly in the UK, there's a lot of use of the NEC, a lot of design involvement with contractors. When you're in Africa, we've been very influenced by the price-based contracting strategies, and we need to start thinking about getting to the cost-based strategies to achieve what we need to achieve. So I will then hand over for the concluding remarks from the chair.
Oh, thank you so much for the presentation, and that's really put in a very, very good perspective, Ron. Thanks to the presenter. I know we have very little time to sum up everything that we have on the slide, but we did fantastically well. So, quickly in summary, first off, we should understand that early engagement is very, very crucial to be able to achieve all these propositions on lean concrete design. For instance, if you're starting out a design, it is essential for us to put forward and demonstrate the benefit of lean concrete design to the contractor, and this is very essential to start this at the early stage of the project. That's where we can actually have a very good amendment, and maybe possibly by challenging the brief with what is presented by Jenny, where 5 kilonewton per meter square, if you actually look at it from a quantitative aspect, you could like tailor what the load demand for the building is and ensure that the right load is actually used for your design. And all the discussion today, I know it is in line with PAS 2080. That's PAS 2080 code, which encourages all designers to make sure that you use less stuff. And by building nothing, if it's not necessary to build at all, don't build. And if you need to build at all, make sure that you build less, or build cleverly, or build efficiently, and eventually make sure that on top of your agenda is to minimize material use. and waste. So thanks so much for the presentation once again. We are expecting that we should have a comment, question. If you have any question, delegates, if you have any question, you can drop these questions for us, and we'll try as much as possible to do justice to these questions. And maybe for the ones that we could not maybe possibly provide answers to right away, we can take them, and maybe you can send an email, and we'll try as much as possible to provide you a response to your question. So on the screen, we should be having, okay, I think we have a feedback QR code initially on the screen. I'm not sure if we still have that again now, but for feedback, I know we can have. Yes, okay, yes, that should be back up. So we can make use of this QR code to provide feedback, and for the survey that's contained in the QR code itself. So any reflection from the participants? Any further reflection on the presentation before we take questions from from. Okay, yes, I think we have a question here. Okay, so a question that I have here is a question. This question is for Cam. Cam, confirm you can hear me.
Yeah, I can hear you.
Fantastic, fantastic. So we have a question from the participants here that the case for using 2-meter waffle slab was very compelling to me. Why did the contractor still go ahead with the traditional 0.8 by 0.8 meter one? So can you help?
Yeah, I mean that is a good question, and I'm not sure I'll ever really know the answer to it. We were working with one contractor throughout the process in a way that Ron was discussing, but late in the process we had a new contractor brought in who was much more kind of they wanted to do things the way they were used to. I don't know, perhaps they had these waffle molds, the kind of standard waffle molds themselves. They're a very large contractor. They're used to working with it. Maybe they had the system, access to it. They weren't interested in ordering something bespoke, and the risk of procurement, the risk of procurement delaying the project. Yeah, that's. I think that's the best that we can that I've come up with to date. But yeah, I just want to kind of reiterate more of what Ron said. I think just getting contractors on board early and making sure we're all working towards the same goal is so important. Thanks.
Okay, thank you. That's an excellent one. Thank you, Cam. So we have the next question, which is for me. What are the differences in culture? What differences in culture do you find between the African continent and the UK in terms of sustainability? Okay, I think the shift in the peak for everyone globally is the same. And because of the recent awareness that is being brought upon us, that our action and inaction, they are contributing to what we experience globally, global warming. So why COP26, if I'm not mistaken, COP26 from the outset of the Paris Agreement, every organization too from in Africa before I left, they have taken on board that target of 2050 to go net zero. So basically, but if we want to look at sustainability in terms of material provision, I know we are still in Africa not really having maybe ratings, proper rating, EC rating for materials. These are data that I believe if we can, like in Africa, work towards getting materials rating properly, then we can actually make use of, we can take advantage of some of existing information for sustainability in other parts of the world for Africa. But I remember working on a project in Africa, back in Africa as well, where I was able to justify to clients right way before now by using some of the structural tools for carbon estimation on iStruct website, and I was able to present to the clients the options, and they actually eventually went for a more sustainable design, and we carried that out. I hope I'm able to provide you a good response. So thank you.
As an African, can I add to that?
Yes, please go ahead, Dr. Ron.
Look, as far as I'm concerned, the way I explain the differences is one must think about the priorities, and I've always cast it into a green and a brown agenda. In the developed countries, the problem is overconsumption. In the developing countries, it is underdevelopment. And something that's always stuck with me is Gandhi said many years ago that poverty is the biggest polluter. So when you're looking at your sustainability, you've got your economic, social, and environment. And depending upon where you are positioned, some might have a higher priority than the other in certain types of projects. So to me, that is where the fundamental differences would be. We're all in the end trying to achieve the same goals.
Spot on. Thank you. Thanks so much, Dr. Ron, for your contribution. So we have one question again here, and this question is for Jenny. What can graduate engineers do to equip ourselves with the skills to tackle the climate crisis, considering there is not much big decisions we can make as we are very early in our career? Did you get that, Jenny?
I did. Thank you,
Okay,
Gabriel.
fantastic. Yes.
I think you can, as a young graduate engineer, you can you're closer to being taught things. You're closer to having your mind. Your mind isn't made up about certain things, so you are more able to see new things coming in, and have been exposed to them possibly at university. And what you can, I think what you can do, and it's a long time since I was a graduate engineer, but I can remember a long time ago having it was up to me to decide say you're doing a building. Obviously it's different for other projects, but if you're doing a building, you will be given a floor slab to do, or the
okay, like we lost Jenny for a second there. So, anyone interested in continuing with this question? Can you give it a try? So, like a graduate engineer, what the consideration perhaps is considering the level of influence that a graduate engineer has. How can they as well challenge brief, or possibly contribute to
by choosing a
lane
different
design?
system?
Oh, okay, Jenny, we lost you for a minute, Jenny, please.
Okay, I don't know how much of that I lost. All your pictures went away.
Really?
You can, as a graduate engineer, you have the ability to decide to be more efficient than not, and that's one of the things that you can do and learn. What works and what doesn't. So, saving 42% from just doing 3 different. You're not changing the concrete. You're not changing anything. But you are making a difference by quite a long way. As structural engineers, we can make a big difference.
Yeah,
And
fantastic.
reduce costs.
Correct.
Yeah.
Dr. Ron, you want to add something?
I just wanted to say as well, you also can have the influence of reducing cost. So
Yeah.
I think it's always a challenge that one has got to say, even though that you've got your constraints, work to what you can and learn. And I think that's the big issue.
Okay, so thanks for that. Uh, Another question for us, here, Cam, I think this is for you. And the question goes thus: do you find that concrete strength and cement types available in Luanda or Africa more generally lower or limited? How does this impact lean design?
Yeah, absolutely, it does. I mean, it depends where on the continent you're working. I mean, we work on a number of projects in Rwanda and East Africa, which is a different situation to Angola, where the cement industry is actually much better established. I'm sure in South Africa as well. And so, in Rwanda, I will design with a baseline of a kind of C2025 concrete because I know that that's what's easily achievable within, general cost and budget. Whereas I think in Angola, we were using a much kind of maybe like a 28-35 mix from memory. And so, yeah, of course, it affects things. But I think optimization is possible no matter what strength of material you're working with. And it's so easy just to throw concrete at a building. And just to build off what Jenny and Ron said, I think as a graduate engineer, getting to know the standards and understanding where you can push and pull and know what those limiting factors are, understanding fire and what that does to your design and how you can then pull and push on that, I think is important. And that's achievable no matter what strength of concrete you're using.
Okay, thank you for that, Cam. So I hope that answers the question for the requester. So another question here as well for Cam. Sorry for putting you on the hot spot, but the question has just come in this way. So the question goes thus: when calculating the reduction of carbon, was the impact of shipping the specialist formwork accounted for?
Yeah, it was, and I think as highlighted in the question, because the formwork, the kind of typical formwork isn't actually manufactured in Angola, you're shipping this material from Europe or Asia, no matter what the case. And so, yes, we kind of did consider it, but it kind of came out roughly equal in both cases. You could argue that maybe if the formwork is already there in the country, then you can take some of that off. But there was enough of the formwork needed that, it's reusable, but only a certain number of times. So you have to kind of balance that effect. And also, to be completely honest, when you can ship to a port, when you can put things on a boat and ship it in shipping containers, we found often that the effect on embodied carbon associated with shipping by sea is actually quite small compared to the effects of cement production. When you get into air freight and overland transit, it's very different, but Luanda is on the coast, easily accessible. Yeah. Thanks.
Yeah. So thank you. Thanks so much, Cam, for this. And I hope this will be the last question anyway. We still have one more to go. Actually, the question is for anyone, but I'm going to allot this to Jenny. So one of UK's government's plan is to boost the supply of new homes through encouraging MMC, that's a modern method of construction. Um, how does lean concrete design technology, how does it play in this area? Does it accelerate or improve the construction output? So that's a question. Jenny, over to you.
If you use a modern, if you use a system which can be made to be as efficient as possible, so you can use some of the precast solutions or the blockwork solutions that are being used used for housing in the UK, they can be designed down. I mean, normally when we're designing a building, we design one building and then we go and do another one building and then we do another one building, and each time we're busy having to not quite reinvent it, but we're getting information from our last one, but it's not the same thing. Whereas with housing, you can do, apart from foundations, they're all sort of very, you can do things that are similar, which means that you can reduce down and have lean design, because you can put your energy into getting it as lean as possible, while still maintaining it as being robust and safe.
Yep, spot on, Jenny. Thanks a lot. And basically, I think MMC in itself, once you're having prefabricated units, you have modular units as part of your construction, it's in a way in itself accelerate construction program. That I think, yeah, is very correct. So,
Let me
those are
take it from a
just,
different angle. Let me
yes,
just take
please
it
go
from
ahead.
a completely different angle.
Yes.
I had the privilege and the experience for, well, it's more than a decade now, of South Africa decided to build two new universities. Now, the two universities were in provinces where there weren't universities, and we started from scratch with the idea that they would every year grow and grow and grow. Now, had we used the traditional or the common way of procuring in what I call the hit and run, where you put a building out or you put a package out to the market, person does that thing, they do their job, off they're gone, they're going to maximize their gain because there's no long-term relationship in it. We went with framework contracts on high-end academic buildings, which were not modularized or the same or doing the same thing all the time. And by having the same team working for maybe a 4 to 5 year period together, you got efficiencies going all the time. You got less waste, you got everything because you're working as a team. And what Jenny was also talking about is just looking at the designers. You're designing a building and then you're designing the next. But we must bring the contractor on board, because as the contractor works with you, and you move from project to project, so the learnings from both design and construction get optimized and we have less waste as we go forward. So I think we've also got to look very carefully on how we put our projects together, how we procure them, and how this buying and selling relationship works. Thank you.
Yeah, I agree with you, Ron. Very much so. The
Yes.
contractor is an enormously important part of this.
Yeah, correct. So, thank you. Thanks, everyone. We have just some few more minutes to go on this presentation.